Welcome back to this session on network analysis. So, we will continue with some of the ideas that we have discussed in the last lecture. So, to start off, I would just briefly recap the concept of eigenvector centrality that we developed on the last lecture. So, if you look at the slides, I have written exactly whatever we have done last day on the slides. So, the basic thing that we saw was that if x t is the popularity value at some time t, then we can express x t in terms of a t into x 0. This is what we have already seen. Okay. So, this we call equation 1, say for simplicity. Now, what we have further said is that let us express x 0 as a linear combination of some eigenvectors of the matrix A, the adjacency matrix A. So, then one can write x 0 as nothing but the sum of some linear combination of some of the vectors, okay, of the adjacency matrix, where V I is an arbitrary eigenvector of A, right. This is what we wrote last day already. So, further from the eigenvector equation, we all know that A v should be equal to lambda v, where lambda is the eigenvalue corresponding to the eigenvector v. So, now if we multiply both sides of this equation by A, once again we have A into v is equal to A into lambda into v. That should be equal to lambda into A into v once again, that is nothing but lambda into v, that is lambda square v. So, continuing like this for t times, we have this would imply A t v should be equal to lambda t v, right. So, this is what is we call equation 3, and let us say that we call this equation 2. The equation x 0 is equal to sum of C I V I as equation 2. So, from 1, 2 and 3. So, now from 1, 2 and 3 we can write the following expression: x t should be nothing but equal to lambda I t C I V I, right. Now, we will do a small trick out here. What will we do? We will divide both sides by lambda 1 t, where lambda 1 is the principal eigen value and the corresponding principal vector is say v 1, right. So, then you can write this as nothing but lambda 1 power t C I V I. Now, if we have gone sufficiently many number of steps, so we are talking in terms of thermodynamical limits, that is when T is very, very large. So, the point after which there is no change, there is no significant change in the popularity. So, at that point we will have limit. So, we will have a limit on T, it really goes to large numbers, we can put on both sides this limit. Right. So, this, what does this tell you? Now, for I is equal to 1, this value, the value here changes to 1. So, you have C1 V1 plus numbers which have a fractional prefactor, okay, powered to some infinite power. So, all those fractional prefactors that are powered to some infinite power goes to 0, only C1 V1 remains. So, this tells you that the popularity converges to the principal eigenvector of the adjacency matrix A. So, that like kind of completes the idea of eigenvector centrality. So, basically in a nutshell, what you need to remember is that if you have to compute the eigenvector centrality of a network, then you, for that network, you have the adjacency matrix say A and you compute the principal eigenvector of A, say that is V1, which corresponds to the eigenvector centrality. This V1 corresponds to the eigenvector centrality of the nodes. Centrality of the nodes. Fine. Okay. So, all this time we were discussing mostly in the context of undirected networks, where edges are not directed. Okay. So, this entire exercise that we did in for computation of eigenvectors, okay, is for a undirected graph. So, the adjacency matrix A is assumed to be symmetric. Okay. So, all this explanation that I have given you so far is under the assumption that the adjacency matrix that we are considering is symmetric, that the graph is an undirected graph. Now, the immediate next question, if you look into the slide, is how to convert this definition in the context of a directed network. Okay. Now, there are, as soon as you try to do that, there are certain problems that crop up. Okay. And one of the important problems is what I have shown in the figure in this small network that I have described here. So, what happens is, think of the node A. Now, this node does not have any integrity, its integrity is 0. So, that means the centrality value that this node will have is 0. Then the node B, consider the node B, this has only one integrity from A. So, this node will also have an centrality value of 0, because A has a centrality value of 0, which is actually borrowed by B, and that centrality is also 0, and in this way it continues and propagates over the entire network. So, the entire acyclic part of the network actually, for all the nodes that are part of that cycle of that network, have a 0 centrality. So, this is a very big problem when you try to translate the concept of eigenvector centralities for directed networks. So, I repeat, the problem is very simple. So, you have this node A here which do not have any integrity. Okay. So, that means since it does not have any integrity, its centrality is going to be 0. So, if its centrality is going to be 0, then the centrality of B, which is solely completely dependent on A, is also going to be 0. And in this way, anybody whose centrality is just dependent on B, is its centrality, the centrality of that node is also going to be 0, and this will continue until and unless there is some cycle in the network. So, this is a problem when you try to convert the definition of eigenvector centrality for directed networks. So, what could be a solution? So, what we try to do is we try to sprinkle some initial popularity to each individual node. Fine. So, since this is a problem, so now if we sprinkle a very small equal centrality to all the nodes, so we do not discriminate any node. So, we try to sprinkle a very small tiny centrality value to all the nodes equivalently. Now, we start from that configuration. So, then in that configuration you can immediately see that A's centrality will no longer be equal to 0. So, then you have to, therefore, if you do such a thing, then you have to readjust the formula that we introduced last. So, now again we can write x t, or say for a particular node, let us write for a particular node first, x I should be, now we are rebalancing things. So, here in this formula what we have brought in, it looks very similar to the previous formula that we have introduced for the eigenvector centralities, but then we have brought in two important changes. If you look carefully, one is this parameter beta here and the other is this parameter alpha here. So, both beta and alpha are constants. This is the first premise. The second thing is beta is the small initial value of centrality that we give to each node. So, beta is the initial small centrality that we actually give to each node equivalently, and alpha actually is the readjustment constant so that the entire formula remains balanced. Okay. So, since you are introducing this beta component into the formula, you have to accordingly rescale the other part of the popularity. So, one popularity is inherent, that is given to me, that is sprinkled on all of us, and there is another popularity that is coming from the neighborhood. So, these two has to be rebalanced again in order to keep the formula equivalent to the previous case. Okay. So, now given this, we can immediately write the notations in terms of x t's as functions or in terms of vectors and matrices. So, now x, let us say x is the vector, popularity vector. So, this is like x1 is the popularity for node 1, x2 is the popularity for node 2, and so on and so forth. So, this is my vector of popularities. So, from here you can, given the formula that we have written just now, we can immediately write the following expression as I have already written also on the slides: A alpha A x plus the beta into 1, where 1, the darkened one that I am writing, the bold 1 is the vector of all ones. Fine. So, you can therefore express x in terms of alpha a, again the vector a x plus the beta factor, which actually is nothing but the initial popularity that you have sprinkled on each and every individual node. Now, this if we try to readjust and write express x as the subject of the formula. So, expressing x as the subject of the formula, okay, we can write x is nothing but beta into 1 minus alpha a inverse, and there is this vector of all ones. Let us denote the vectors by the vector sign, it would be easier for us to note. So, fine. So, now see, from that original formula we have come up with an expression to find out the exact value of popularity given the constants alpha and beta and the initial popularity beta, the other readjustment constant alpha. Given these two and the adjacency matrix of the network, you can immediately compute the popularity value x. But then just a point of note here, that computing inverse, this is the identity matrix, inverse of matrices is difficult. So, it is better to go by the, thus it is better to compute using the iterative equation, which in this case is again very simple. You can write x t is equal to nothing but alpha a x t minus 1 plus beta, and then there will be a point after which x t will change no longer, and you will have a expression for the final value of x t. Okay. So, all of these ideas are borrowed from the first definition of eigenvectors. Then we are gradually incrementing that same idea, we are building up on that same idea and developing better and better metrics for application in different network settings. For instance, this particular development is in the settings of a directed network, and this particular centrality is termed as, by the name of the inventor, Kurt's centrality. Okay. So, now since we are talking about eigenvector centralities, Kurt's centrality, directed graphs, there is one thing that actually is indispensable and needs to be discussed in this context, and that is like the World Wide Web graph, and in the context of the World Wide Web graph, how are the web pages ranked. Okay. So, all these initial settings that we have been developing so far in the last lecture and today's lecture is in the direction of building the idea of how to rank the web pages in a World Wide Web graph. So, basically in a World Wide Web graph you will have nodes which are pages, say page P1, page P2, page P3 and so on. So, in this way you have a World Wide Web graph, and if there is a hyperlink from page P1, you draw a directed edge like this. There could be another hyperlink, say from page P2 to P1, you draw a directed edge like this. Okay, and this is a typical representation of a World Wide Web graph. Now, the question is, like all of us have been using Google search engine almost every day and multiple times a day. So, and probably many a times a question have come across is like, when you search using a query term, there Google returns you back a bunch of web pages. Now, these web pages actually are ranked in some way, and this ranking actually is done in terms of the importance of a particular page, and this importance is measured using some formula which is very similar to what we have just now discussed, which is very similar to cut centrality, and this formula was developed in the framework of the very famous algorithm called the Pagerank. Okay. So, Pagerank basically tries to determine the rank of a web page being displayed in return to a query on the search engine. Fine. So, this is what this algorithm actually tries to assign importance, okay, to each individual page, so that whenever there is a query, there is a search query, the pages that are returned could be actually sorted in terms of their importance. Okay. So, the basic idea is again same as we have discussed for the case of the eigenvector centrality. If you look at this slide, I give a very simple example of a small snapshot of the World Wide Web. So, what you see here are a few nodes marked like A, B, C, D, etc., and the size of the node is actually the extent of popularity. It expresses the extent of popularity of that particular node. You see that the node C has only 1 in degree, but then you see that the popularity of node C is quite high. This is because node C is actually pointed by node B, who himself is very, very popular. Okay. So, this is the basic idea of the eigenvector centrality that we have already discussed. So, since node C is being pointed by a already highly popular node B, that is why node C's popularity automatically increases. Okay. Whereas, take for the example the case of node E. The node E here has a lot of in degree, but each of these nodes that point to node E are not themselves very popular. So, that is why node E is not actually very popular. So, even if it has a very high in degree, it is not actually very, very popular. Whereas, in contrast, node C, which has just 1 in degree, is much more popular by virtue of having one very popular person pointing to node C. This is the idea that we have already discussed. I have just illustrated the same using this example on the slide. So, then the question is, how was PageRank defined? It is again very, very simple. So, even before we go to that definition, the quantitative definition, one question that can immediately come to our mind is how to make our own web page. Suppose you have hosted a web page, what could be a criteria to actually make your web page important or popular? So, this is a very important question, and various companies have been working in order to help the promotion of certain web pages. Okay. And the crux is the following. So, if very highly popular websites, say for instance Google, Yahoo, MSN, etc., are pointing towards your website, if there is a hyperlink from all these websites to your website, of course this is a dream for every person, to your website, then immediately your page rank, your importance actually rises, and whatever search term is fed to the engine, there is a high probability that your page is retrieved back and shown to the user. Okay. So, this is the basic idea. So, now with this basic idea we will turn to finally defining a quantitative measure for the page rank. Okay. Again you have say the popularity of a particular node being expressed by xi. So, then you can write here xi is equal to alpha, the same type of expression that we have already written, aij xj plus beta, but there is only one small difference from the cut centrality, in that what you do is you now divide the popularity of the node xj by the total out degree of xj. Suppose there is this node j, it has an out degree of kj out, and say the popularity of xj of the node j is xj, then each of the individual nodes that j is pointing to, one of these is actually the node I with popularity xi. So, each of them is getting a fraction xj, is receiving a fraction xj by kj out from the node j. So, this fraction of popularity from node j actually is given to node I. So, you basically appropriately normalize the popularity of xj and distribute it among all its neighbors. Okay. That is the only difference from the cut centrality. Cut centrality did not have this normalization. Now, one problem that immediately comes up is that if kj out is 0, that is the out degree of j is 0, that means this would immediately say that j will not be able to contribute to the centrality of other nodes. Okay. This will immediately say that kj will not be, so the node j will not be able to contribute to the centralities of any other node. So, in such cases we assume that kj out is preset to 1, okay, in order to make our computations easy. So, in all such cases where kj out is 0, because there is no out, because there is, so xj will be the popularity of j. So, this component will actually go to 0, because it will contribute 0 popularity to all other neighbors. Okay. So, we set kj out to equal to 1, so that we avoid division by 0. Okay. So, in that particular situation we can write again the vector form of the equation as a alpha a. Now, since this kj out is here, we have this matrix D inverse x plus beta into 1, where these are all vectors. So, now we can again express the vector x as the subject of the formula, and this will give us D inverse, where D inverse, where D is the diagonal matrix containing all the out degree values. Okay, where D is the diagonal matrix containing all the out degree values, and dii is nothing but max of kj out and 1. If kj out is 0, then it is set to 1. Thank you very much.